Okay, let's go over that electrical mesh problem with full algebra one more time. I'm going to have the full algebra, but at the very end, we are just going to keep it at A and B because you'll see. Um, for a problem like this, I mostly care about how do we set it up. So, for the problem statement in the handout, they want you to find out the transfer function from your input to your output I2 of t. And I'm going to make the speed of this go a little bit faster. So the steps we're going to do for our electrical systems, we want to set up our KVLs for each loop. We want to make sure to use impedances when it makes sense, and we want to use KCL to limit the number of current variables that we need to deal with. So for here, we only have one defined so far, but just like we had multiple variables, if you think about dummy variables, in electrical circuits, we're going to see lots of dummy variables in the sense that we want to make sure that we can represent what's going on and set it up in a way. So here we have I2, and we're going to add some dummy variables, I1 and I3. So we want to make sure that we have at least one variable for each loop because that's going to help us solve these problems. And we might want to talk about the current for every single element. And so what we could do is just give those definitions, name them after the elements they pass through, and then we'll worry about isolating them with KCL afterwards. So we could say there's a current going across the capacitor, current going across the inductor or the resistor, and the direction doesn't matter except that we need to choose a direction and stick with it. So I'm going to draw one, I'm just going to call them after the elements they cross, and we'll simplify them out later. So let's skip ahead. Okay, so we're going to have three loops. We're going to say we have loop 1, which starts with I1, loop 2, which starts with I2, and loop 3, which goes across I1 and I2 from the voltage source. Now we want to set up our voltage loops. So for loop 1, we're going to say that we have the impedance of that first loop, and so that's R2 plus L1S, that's multiplied by that first current. Then we have the second impedance, 1 over C1S, times the current, and we could also say plus R1, IR1 for that last one. All of these voltage drops are equal to 0. Can do that for the second loop as well. So we have 1 over C2S, the impedance of the capacitor is 1 over CS. L2S, inductance of a inductor is L2S. And times IL2, we don't know what that current is yet, that's okay. And then finally, we've drawn ICL as going from in the direction that opposes our loop. If it opposes our loop, we're going to draw it as negative. So we'll say minus 1 over C1S times ICL. All of these should become 0. Now, finally, we're going to do the last loop. For your sum of your voltage, if you say the sum of your voltage drops equals 0, you could also treat a voltage input as negative, or you could just say the sum of your voltage drop is equal to your voltage that's added to the system. Whichever way makes most sense for you is the way you should set it up. I'm going to say that our voltage drop is equal to the voltage that's supplied because that gives the same end. And here we're getting ahead of ourselves a little bit. So let's... nope. So, we're just going to keep going through. Okay, if we use impedances, we have been doing that because we have L1, LS, and 1 over CS for each one. We could also combine R2 plus L1S to an impedance Z. So I call it ZRL. It's optional. You can use your personal choice for how much you want to incorporate that. And then we can combine currents. So I'm going to go back a little bit before we press play. I didn't add enough stops to this. For combining our currents, we're going to look at each node. So for R1, we're going to have IR1, IC1, and IL2. For IR1, we look at the node with IR1, I3, and I1 because we want to limit our currents to just the number of loops, and so I've kind of isolated the ones using colors for which ones we care about. So if we use Kirchhoff's current law, then we have IR1 plus IR3 is equal to I1. And in doing so, we can say that IR1 is equal to I1 minus I3. We could do that with C1, I1 minus I2, and with I2 minus I3. So for each node, we can say current going in is equal to the current going out, and making sure that we end up with only the number of currents as we have loops. Because that's, again, a step we should do in some order in order to help us solve these problems. The steps I'm giving, you can do them in any order. I just chose one to move through it. So now the next step is just going to be a ton of algebra. I'm going to take these equations, since we have it all set up, we don't need that circuit anymore, and now we're going to talk about how we can go through algebra if you need help with that. And here, what's going on is, let's go here. So here we have the currents we were given, we have our equations that we have before, and now what we can do is we can replace those little currents that are named after nodes with just I1, I2, and I3. So place them all, and that way we have our equations just in terms of those three current variables. We have four dynamic variables, so our input variable as well as the three currents, three equations. That's all we need for to find our transfer function. The rest is algebra, and it gets a little bit painful. So we're going to do an example. I wouldn't have something this complicated for you on an exam, just because this is a lot. 3 equations, 4 unknowns. I don't want to test you on algebra, so if at this point you just said, too much algebra, and then just told me what the transfer function would look like, that would get you the vast majority of the points. But let's slog through some of the algebra, because it's a good skill to have. So, for our algebra, we want to make sure that we keep our goal in mind, so we're not going in circles. We want to gather all of our similar dynamic variables and isolate the ones that we are not interested in. So they're unimportant to us because we decided that that's not what we care about. So our goal is I2 over EI, because that's the transfer function we're asked for. Our unimportant variables are I3 and I1. So we can take those equations that we had before, and in doing so, we're going to keep that goal in mind and start to isolate everything. I'm going to say we need to isolate I3 first, because if we look at our third variable, in our third variable is going to be where third equation, we have I1 and I2. So we're going to find I3 in terms of I1 and I2. Then we'll find I1 in terms of I2. And finally, we'll be able to solve our full answer. So we'll have equations 1, 2, 3, and go through this method to isolate I3 and then I1. So for I1, we're going to be able to take that equation, gather all the like terms. So everything multiplied by I1 we'll have together. And I'm going to want to isolate I3, so we'll have I3 on one side. And we can have it completely isolated by dividing by R1 on both sides. For equation 2, we could do the same thing. Gather all the I2 terms, gather all the I1 terms, and then isolate that I3 term and divide by that L2S in order to have everything in terms of I3. With these two equations, we can combine them, set them equal, because we have equations I1 and I2, and that allows us to have everything in terms of just I1 and I2, and we'll be able to solve for I1 as in terms of I2. Then replace it in that third equation. I'm going to zoom up the playback speed a little bit. So we have this equation in terms of everything in terms of I3. We don't care about I3. We can write it down because we know that we solved everything in terms of I3. But now what we're going to do is we're going to rearrange this to have all of the I1 terms on one side and all of the I2 terms on one side. And so you would do that by multiplying by R1 and times L2S on both sides, so we can get rid of those terms, gather the like terms, so we have everything in terms of I1 and I2. And I'm going to also publish the PDF notes for this so you can see it in detail. but this is just to walk through it all. And if you say cheerio to me and let me know you've watched this video, that'll be nice, because otherwise I just wasted my morning. But it's a little Easter egg. I'm going to have students say cheerio to me, and I'll have no idea why. But let's go through, and then, we have that L2S over C1S. We have all these terms. Now we're going to just call this A and B, because there are so many variables here. And we'll combine that with that third equation up top. So we can say that A is everything on the left side of the equation, B is everything on the right side of the equation, except for I1 and I2. Plug it in, so that way equation 3 can be represented in terms of ZRC, B, A, and variables that we've already been given. So from this point, what we would do is we'd be able to look at those B and A so that we could solve through, simplify them some more, and have our equations in terms of I2 and E2, which is what allows us to have EI, which allows us to have a transfer function, and we can have it in terms of B and A. And if we want to, we can start simplifying A and B by going through the process of factoring out all the terms, multiplying by C1, multiplying by C2, and eventually, as you'll see, you'll have a ton of terms that you could just plug back in. I'm going to say at this point that it's doable. I'm not going to give you something with this much algebra on an exam, but if I did, you would know how to do it. The question is, how much time would it take? And that's not how I want to use your time. So I hope this helped for some algebra, and I will see you in class. Stop recording. The button's not working. Oh no.